Hey everyone, welcome back to another topic revision video on CIE A Level Physics. Today we're going to talk about the forces, density, and pressure topic. So the first two subtopics of this are turning effects of forces and equilibrium of forces. So this is a simple topic, not quite a lot complication in it. So we know that weight of an object is the force of gravity acting on it. We are already familiar with this. But where is that force acting? That's acting at center of gravity. So center of gravity it is the point through which the entire weight seems to act. You can actually write this one also. Weight of an object acts at a single point through which weight of an object acts. So even if you forget about this, that's seems to so weight acts or acts, whatever you want to write it, but keep the grammar correct. Right. Okay. Now, this was just the center of gravity. We know how center of gravity can help with the stability. So, the next thing is the moment of a force. So, moment of a force, just to write the concept, not the definition yet, it is the turning effect of a force. It's simply the turning effect of a force about an axis. So axis could be any point, and force could be acting about this. This can be the distance between the line of action of force and the point. So obviously there has to be something connected between the point and the force. This doesn't work this way. So if the force is acting and there is some axis, a point, there is going to be a turning effect of that force. We also call this pivot. Right. Now the definition itself. So definition, we are already familiar with this from IGCSE and O levels, but a good thing to go it is. It is defined as the product of force and the perpendicular distance between line of action of force and the pivot. Now, to understand what this actually means, we in IGCSE and O level, we were familiar with having this type of force where the axis, or sorry, the line of action, this is the line of action of this force along this line. So this is already perpendicular to this. So the perpendicular distance would be this one. This is the force, this is the perpendicular distance between them. But what if the force is acting at an angle to this beam or whatever this is. So for example, if we have this is the pivot, and maybe, for example, the force is acting, let's say this way, for example. So in that case, how would we find it? So what we need are two things. We need perpendicular distance to the line of action of force. We can do it two ways. I will copy it just to show you the difference between them. The methods are almost like the result would be identical. So one thing we can do, if we have the theta, we can find out the component of that force, so F sine theta, and then we can multiply that with the distance between the point of action. Let's call this point of action of force with the pivot. So this would be D. So the product moment over here, this is FD. Over here, this would be F sine theta times by D, which would be just written as FD sine of theta. Another thing which we can do over here, so if the distance between the point and the pivot is D, and we extend this to over here, this is the line of action of force. So basically what we can do, we need a perpendicular, so this can be our perpendicular distance also. Let's call this R, for example. So if this is the angle theta, this would be angle theta, and since this is going to be perpendicular, so we have d sine theta. So R would be d sine theta. Simple trigonometry over here, nothing. So again, you will have F times by d sine theta, and as you can see, it ends up being the FD sine theta as over here. All that means is that it's the perpendicular distance between line of action of force and the pivot. Now, some books have that cos theta case also, but it's up to you. It's up to the question itself whether this angle is given or this angle is given. So if this angle is given, for example, let's call it gamma, in that case, it will be cos theta. So you have to be very careful how the information is presented. Right, okay. So we did this, we did this. So this is the application of moments over here. So we know that the moment has force and the distance. So what about the units and everything? So units are force times by displacements in Newton meter. So Newton meter. What about nature? Is it a scalar or a vector? It's a vector quantity. How? I think those of you who have studied IGCSE, you might remember that, but although the moment is a clockwise or anti-clockwise rotation, so uh, although, sorry, moment results in clockwise or anti-clockwise rotation, but using the right hand grip rule shows the direction of the vector. Shows the direction of the vector. So what is this right hand grip rule? So basically your fingers are curling in direction of rotation, and the thumb points to the direction of vector, in direction of vector. So basically, if this means is that, for example, you have clockwise rotation. When you apply the right hand grip rule, your vector comes straight down. And if you have anti-clockwise, so for example, anti-clockwise rotation, so this is this way, your vector comes out this way. So vector quantity because of that. And also remember, this both of these, F and D, they are like vectors. So this is basically a cross product of two vectors, or vector product, because the product itself, moment, is a vector, as you can see this. Okay, all right. The application of moments also has one important point. The sign convention. So usually what we do is we assign, it's a convention, anti-clockwise moments are assigned positive and clockwise moments, sorry, are assigned negative. So what that means is, for example, we have, and this only works, sign convention is for sum of moments. Sum of moments. Like either way you're doing sum of moments, anti-clockwise moments can be taken positive, clockwise can be negative. So for example, you have a beam. This is a force, let's say 50 Newton, and this is a force, let's say 75 Newton. This distance is, let's say 1.5 meter, and let's say this is also 1.5. No, let's call it 2 meters. Okay. So notice over here the force that will cause a clockwise rotation is 50. So sum of moments, capital sigma, anti-clockwise one would be this one. So force times by distance plus force times by distance. This is going to be 75 times by 2. This is positive. Negative clockwise 1. 50 times by 1.5. So 75 times by 2 is 150. 50 times by 1.5 is 75. Yeah, so this is going to come out to be 75. The units would be Newton meter. Now we could have multitude of forces over here. We could have tension forces. We could have anything else, but that would be just simply just adding these forces together. So you could add the anti-clockwise forces together, clockwise forces together. So all you have to remember is that anti-clockwise or counterclockwise forces, we add them positive, and clockwise moments, we add them to be negative. This is just a convention, basically. Okay, so uh, just to go over. Oh, okay, so couple. All right. Now, a term that is usually used instead of a moment is torque also. So torque basically also means moment. Okay, so moment of a force uh, about an axis. So if a question says torque of a force about an axis, that basically means. However, uh, we generally assign or use torque instead of moment for couples. So when we say torque of a couple, we are already familiar with couple, but just a second, I will explain it. It basically means that the moment of two forces about the axis. We're already familiar with what couple is, so we have two forces acting in opposite directions separated by some distance. So this is the couple. The moment of two forces about the axis. Axis can be this, the middle, basically. But we usually, instead of saying moment of two forces, we usually use the torque of a couple. Instead of you saying moment of a couple, we say torque of a couple. Now, how does this work over here? Like, what is the difference between this and this? So basically, if you think about this, this is just simply adding these two moments. So for example, you have two forces, let's say F, and this is also F, and they are separated by, their lines of actions are separated by some distance d. Exactly in the middle is your pivot. So the moment would be, this is causing clockwise, this is also causing, sorry, anti-clockwise, counterclockwise, and this is also causing counterclockwise. So the sum of moments would be F d and d by 2 plus F d by 2. So notice what this adds up to, just simply Ft. So that's why we just simply call it torque of a couple. One thing to notice over here, torque, or simply just a couple of forces, produces pure rotation, no translation. So the action of forces in a couple produces just simple rotation, no translation. So how do we mean by no translation, no rotation, and everything else? So when we have sum of forces, so there's a concept called um, collinear forces, collinear and non-collinear forces. Or like vectors, basically. So collinear forces are whose lines of actions of force are aligned. So lines of action of forces are aligned. That means we can add them right away, whether they're opposite to each other or going in the same direction. So for example, this way, that they are acting along the same line. So the point on which they are acting basically lies along the same line. Maybe they're acting this way or somewhere this way. So F1 minus F2, F1 plus F2, either way, their forces are, the lines of actions are aligned. So this is the collinear. So in this case, you have F1 plus F2 resultant force, and in this case, you will have F1 minus F2. But when you have non-collinear forces, we already discussed how to add them, but just to show you that these were the non-collinear. So for example, these ones are non-collinear, for example. We can still add them through vector addition, but these are non-collinear. They can be passing through the same point even, but they will still be non-collinear because they are not, their lines of action, the forces are not aligned. So we will find the sum through vector addition. Now, notice one thing over here. In the couple, these forces are not along the same line. So these forces do not, their lines of actions do not coincide. Okay, so their lines of action do not coincide. If their lines of action coincided, so, oh sorry, no, wait a second. If their lines of action of force coincided, then we could add them also. So for example, if this is F, we could add them. But since their lines of action of force do not coincide, it produces a sort of rotational effect. So whenever forces are separated by some distance, it produces, there's a tendency for a rotational effect. So a couple consists of two forces equal in magnitude but opposite in direction, whose lines of action do not coincide. And now the definition for this torque of a couple, basically. So torque of a couple is defined as the product of one of the forces and the separation. Or you could also say and the perpendicular distance between them, and the perpendicular distance between them. That's it. And remember, we said that we call it torque of a couple, not a moment of a couple. Right, so this is the couple. So, and define and apply torque of a couple also. So just like normal moments, we can have counterclockwise couples also, clockwise couples also. Unit for couples is the same as Newton meter as before, and just like the moments, it is a vector quantity, and the direction of that vector can be found from right hand grip. Now, moving on to the principle of moments. Yeah, principle of moments. So, we said that when you have a beam like this and you have some forces that cause clockwise and some forces that cause anti-clockwise. So this force is causing anti-clockwise force, let's call it FA, and this is FC causing clockwise rotation. Whatever their distances from the pivot are, if the moments are equal, doesn't matter, we could have more forces over here. If the total sum of moments is zero, the body will be in rotational equilibrium. So for an object to be in rotational equilibrium, that means no rotation happening, the sum of moments about the pivot is zero. Technically, this could be about any point, because if the body is equilibrium, even if you take this point instead of the pivot, it should still apply. So distances, you measure the distances from forces, do the sum of moments, that should be zero. So what that means is we said that the sum of moments, we will have some anti-clockwise moments, and we will have clockwise moments, and we just simply write it as sum of moments. So remember, we took them as anti-clockwise as positive, clockwise as negative, as seen by the negative sign. And this is going to be zero for an object to be in equilibrium, rotational equilibrium. Another version of the same statement is that for a body to be in rotational equilibrium, for a body to be in rotational equilibrium. Now, this key phrase is important. It's not just simply the sum of moments is zero, or the sum of anti-clockwise or is equal to clockwise. It has to be that we are talking about a body in equilibrium, in rotational equilibrium at the very least. The sum of anti-clockwise moments is equal to clockwise moments. So if you just simply rearrange this equation, you will have sum of anti-clockwise moments equals to clockwise moments. But this is just for rotational equilibrium. What about the equilibrium in general? What about the translational equilibrium? We already know for translational equilibrium, we said that if the sum of if the resultant force is zero, the object will be in equilibrium. So condition for equilibrium are now twofold. So the conditions for equilibrium. And this could be any equilibrium, static, dynamic, whatever this is. So the conditions for equilibrium, you can have different phrase and different vocabulary for that, but the meaning behind them is same. That the resultant force for an object to be in equilibrium, the resultant force acting on it should be zero, is zero in any direction, basically in any direction. Although the resultant force covers it already, but just to show that the sum of forces in any direction is zero, and the resultant moment you could also say algebraic sum of moments about any axis or point is zero. So these are the conditions for equilibrium. So the first one is that the sum of forces is zero, and this means sum of moments. So when these conditions are met, the body will be in equilibrium. Right. Okay. Now, how this works for different cases. So you have to remember that even when we're dealing with moments cases, we might have scenarios where we have multiple forces acting. Uh, let's say this is the pivot and this is the weight or the weight acting on this. So this, let's say this is F1, this is F2, this is F3. So if an object is in equilibrium, both of these conditions have to be met. So that means that the upward forces have to be equal to downward forces. So this is the condition for sum of forces in any direction is zero. Notice that although they are not collinear, but we are talking about the translation of a rigid body, so we can temporarily do this because we are talking about translational equilibrium. And the sum of moments, you can have distances, so total moments anti-clockwise, total moments clockwise. You can assign sum of moments to be equal to zero. So this is easy, straightforward. We will see some questions also. For resultant forces, we also have the sum of coplanar forces. We also discussed this briefly in the vectors topic and in the forces topic and the dynamics, sorry, that for an object in equilibrium, now we saw this case before also, but just to go over this. Just one more time. Let's say you have two forces. Let's say this is one force 10 Newton and this is, let's say, 5 Newton force. The resultant force acting on this is 5 Newton upward. So basically this is your resultant force. This is like the resultant. This will cause an acceleration also. But if one of these is angled, for example, you have 10 newtons over here, 5 newtons over here. Actually, this is, let's say this is 10 newtons also. So in that case, we can do the the vector addition principles. Tail to head, this is 10, this is 10. So this will cause a resultant vector to be angled this way. And since these are both the same, the angle would come out to be 45. And 10 squared plus 10 squared whole under root will give us the magnitude. We already saw this in the vectors topic. Now, if you take away from this case now, we know that the resultant force is going to be somewhat like this. This is 200 squared. This is going to be 10 root 2 acting at 45 degrees. Because you have tan 10 over 10, this is going to be 1. Or tan inverse of this is going to give you 45 degrees. Sorry, I miswrote it before. So it's tan 45 is 1, but tan inverse of 10 over 10 or 1 would be 45. Now, what if instead we provide a negative of this force in the original system? So if we provide the negative of this force, exact opposite. So exact opposite of this force would be 45 degrees in this direction and having the same thing. So if the sum of forces for 10 and 10 Newton was this thing, 10 root 2, 45 degrees, and we are providing another third force to counteract that, then that means your sum of forces, since already they become now parallel forces, collinear forces, we can add them each other now. So the sum of forces is now going to be equal to 0. Now, what that means is that instead of this pink one, if we do one slight change, we have this 10, we have this 10, and instead of providing a force in this direction, we can provide a force just like we have on the left side, like this. This is 10 root 2 at 45 degrees to this. So now what will happen is that if you notice, the directions are all forming a closed loop. This is a closed triangle, closed loop. So closed loop, basically. This is an indication that the forces are in equilibrium. The system is in equilibrium. System is in equilibrium. This is a very good way of checking and obviously working numerically also for a body in equilibrium. So if the directions are forming a closed loop, the object will be in equilibrium. All right, so let's practice these concepts by working with some past paper questions. Okay, so let's see this now. A uniform bar of weight 200 newtons, so uniform means center of gravity is in geometric center. This is not a new knowledge, we have already studied this in IGCSE and O levels also. So at exactly 2 meters from over here, from this pivot, you have the 200 Newton acting on it. And length 4 meters is freely hinged on a wall at one end. The bar is horizontal and held in equilibrium by a cable attached at a distance of 0.5 meters from the other end. Cable is at an angle of 35 degrees to the horizontal. What is the tension T in the cable? So you have to remember over here that equilibrium is attained two ways. The sum of forces is zero and the sum of moments is zero. We don't know what the force acting on the hinge is at the moment. We can find that out also, but that for now, this is unnecessary. But just to show you that there is a force acting on the hinge also. So this is the weight and this is the tension. So tension may be acting like this. So just to follow through on the principle, there is going to be a force acting on the hinge. Let's call it force H. So this is how it's acting like in equilibrium for the translational. But the moment wise, that is also happening. So sum of moments, anti-clockwise moments, sum of clockwise moments, and we have this anti-clockwise. So you have 200 Newton times by 2, and clockwise moment would be this thing, T sine 35 degrees, and 4 minus 0.5, so 3.5. So T sine 35 degrees times by 3.5. So all we need to do is to find out T, basically. So 400 divided by 3.5 sine 35. So we get almost 200. The diagram all show a pair of equal forces acting on a meter rule. Which diagram shows forces that provide a couple and zero resultant force? The zero resultant force means the sum of forces is zero, but like in any direction is zero, but there is going to be a moment. This is the definition of a couple. We already saw this, that although that the forces are equal in magnitude but opposite in direction, but since they're separated by distance, that causes rotation. So in this case, resultant force is not equal to zero because they're both going in same direction. Over here, no, this is also not true. They provide a couple and zero resultant force. This is going to be the correct one because you have two forces separated by some distance. This is, as you can see, the forces acting along the same point will cancel out, and the forces have to be, since the forces have to be in the same magnitude, the angle of these forces will cause a different magnitude of force acting this. So this is the only thing that B is the only thing that makes sense. Okay, which single condition must apply for an object to be in equilibrium? Must apply for an object to be in equilibrium. The object has a constant non-zero acceleration. So this is obviously not true. If an object has equilibrium, it has net force. Object is stationary. That is not necessary. There are no forces acting on an object. No, that is also not true. The resultant force acting on the object is zero. That is correct. A kite is in equilibrium at the end of a string as shown. The kite has three forces acting on it: weight, the tension T in the string, and the force F from the wind. Which vector diagram represents the forces acting on a kite? So remember a closed loop of directions. So weight going this way, force going this way, and tension going this way. So A is correct. Weight going this way, force going this way, no. No, and no. So A was the correct one. The directions are forming the closed loop. Four forces act about a point as shown. The forces act in the same plane and produce no resultant moment about B. What is the length xy? That means the object is in, the system is in equilibrium. So what is the length xy? Four forces act about a point P. Okay, all right, never mind. Uh, so we can find out the total forces. Clockwise equals to anti-clockwise. So clockwise forces are these two, 6 Newton, 6 Newton. So 6 times by 7 plus 6 times by 3, both of them are giving, causing clockwise. And anti-clockwise forces are this 5 and 5. But we need perpendicular distance, so remember that. So if this angle is 60 degrees, so we need this distance. We don't know either one of these, so wait a second. So xy, wait a second, wait. What is the length xy? So you have 5. This is also going to be 60, and some length of this, some fraction of xy. There is nothing given over here. Four forces act about a point. Wait, what is going on? Oh, okay. So what we can do over here, eventually what will happen is that we will need the distance between them. That's adding with, because they're both causing a clockwise moment. Even if we add the fractions, we will basically be adding 5 with this length and this length. This will add up to this length. So this is going to be 30 degrees, or either way, or this is 60 degrees, knowing the parallel angles. So if this is xy, this is xy sine 60. So this is going to be 5 newtons times by xy sine of 60. Sine of 60 is going to be under root 3 over 2. So xy would be 6 times by 7, 42 plus 18 divided by 5 times by sine of 60. So the length is Okay, so the length is 13.85, so roughly 40. In which example it is not possible for the underlined object to be in equilibrium? An aeroplane climbs at a steady rate. We'll come back to this. Aeroplane tows a glider at a constant altitude. So steady rate means equilibrium, zero acceleration. So this is in equilibrium. Aeroplane tows a glider at constant altitude does not mean that. So constant altitude just simply means that whatever aeroplane you have, the weight and lift, although the lift doesn't act this way, uh, is the vertical forces are balanced, but there is still a driving force over here. So it tows a glider at a constant altitude. And no, speedboat, actually this would be the correct. Speedboat changes direction at a constant speed. So if it's changing direction at a constant equilibrium, the vector wise it is not in equilibrium because it is changing direction, so velocity is changing. So this is the correct one. Two boats tow ship into a harbor. So they could be pulling it at constant velocity also. And constant altitude does not mean that the resistive forces are not acting. So enough. So not possible just simply means that we have to eliminate the obvious choices. So C is the obvious choice. Which statement correctly describes a couple? Couple is a pair of forces that act in the same direction. No. Pair of forces that act on the center of gravity of an object. No. Pair of forces that act to produce a resultant force. No. Pair of forces that act to produce rotation only. Okay, a uniform beam of mass 1.4 kg is pivoted at P. Beam has length 0.6 meters and P is uh, at a distance of 0.2 meters from one end. Loads of 3 kg and 6 kg are suspended at distances of 0.35 and 0.15 meters from the pivot. What is the torque that must be applied to the beam in order to maintain it in equilibrium? So basically the final difference that the torque must maintain. So remember, center of the beam is this, so that means the weight acting through this 1.4 G. Right. Okay. So let's uh, do the sum of moments. Positive clockwise, positive anti-clockwise, negative clockwise. So anti-clockwise is this one and the weight. So 1.4 times by 9.81 weight times by, this is 0.4, sorry, this is 0.6 in total, and this is at 0.3, so this is going to be 0.1 plus this is um, from the pivot, this is 0.35, so 3 times by 9.81 times by 0.35 minus the 6 kg one, 6 times by 9.81 times by 0.15. Okay, so we need to see what is the total moment over here. That whatever the total moment is, we have to produce, we have to supply or apply in the same magnitude. So times by 0.1 times by 0.35 minus 6 times by 9.81 times by 0.15. So 2.8 Newton meter. So this is coming out to be positive. That means the anti-clockwise moments are greater. So we have to supply or apply clockwise moments of 2.8 newtons also. So D. The diagram shows three rigid bodies, P, Q, and R, being subjected to different combinations of forces. Which objects are in equilibrium? So equilibrium again means sum of forces is equal to zero and sum of moments is equal to zero. Right. So 10, 20. So objects, if you think, if you consider objects along the line, this will cause force of 10. This will cause a force of 10. So this will cause a moment. Oh, sorry, it will cause a couple over here, basically. This thing. So the the collinear forces. So this would cause 20 Newton force over in this direction and 20 Newton force in this direction. So obviously there is a resultant force over here. So no. If we look at this one, 50 sine 30, oh sorry, cos 30 and 50 cos 30. So cos of 30 is under root 3 over 2. So this is also not in equilibrium. Which objects are in equilibrium? Actually, none of them are. So basically over here you have not equal to 0. And even this is not equal to 0. So none of them. Oh, we do have an option for none of them. Okay, all right. All right. An isolated object of negligible weight is acted on by two coplanar forces of the same magnitude. In which diagram the object is in equilibrium? So this is not in equilibrium. This is not in equilibrium. This is not in equilibrium. This is in equilibrium because the lines of actions of forces are along the same line and they can be added and subtracted together. A uniform beam PQ rests horizontally on a support at point S. A rope is attached at one end of the beam. Rope is at an angle 60 degrees to the vertical and exerts a force F in newtons to the beam. What is the moment in Newton meter of the force F about S? So rests horizontally means equilibrium. So uh, this is F sine, oh sorry, no, cos of 60. And the F sine 60, remember, its line of action of force is passing through the pivot. So this will not be counted. We only need F cos of 60. So F cos of 60 times by 2.5 minus 0.3, that is 2.2, equals to the weight. Weight is right over here. The total length is 2.5, so 2.5 divided by 2 minus 0.3. So 2. Wait. Oh, sorry. What is the moment of the force F about X? S. So basically, this is the thing, right? Sorry, I did not see that. So 2.2 times by cos of 60, which is basically 1 divided by 2. So 1.1 F. The cos of 60 is basically 1 over 2. So 1 over 2 F times by 2.2, which is just 1.1 F. Okay, this was straightforward. Okay. Two forces act on an object which diagram represents a couple. So this doesn't because both the forces are in the same direction. This is going to be representing couple because the two forces are as equal, same magnitude, opposite directions, and separated by a distance. B. Okay, the diagram shows a uniform rod XY that is freely hinged to a vertical wall at end Y. The rod is at an angle 60 degrees to the wall. The force F acts at an angle 30 degrees to the rod at end X. The rod has a weight of 3 Newton and is in equilibrium. What is the magnitude of force F? Okay. So 60 degrees. So you have to remember, actually the perpendicular distance from the line of action of force, we already have xy. So F times by, do we have length xy? Okay, we don't have. All right. And the 3 Newtons, since this is uniform, this is half of xy. This is half of xy. And this is acting, we will need perpendicular direction. So this is half of xy sine of 60. Okay. So 3 times by half of xy and sine of 60. Sine of 60 is under root 3 by 2. 3 over 2 xy under root 3 over 2. This is your f xy. Xy get cancelled. So you are left with 3 root 3 over 4. So 0.75 times by root 3, you have 1.29. Okay, so if we do the perpendicular this way, uh, 60, this is going to be 60, this is going to be 30, so 30, so 3 cos of, either way, that's going to be the 3 cos of 30, 3 sine of would be the same. So we can do f of sine 30. So, sorry, we could do that. F sine 30. This would have another 2 over here. This will cancel out. So you will have this. So 3 root 3 divided by 2, 2.5. Finally, one of these, right. Okay, so sorry, my bad, I forgot over here. Okay. Okay, let's take something important. Okay, now let's do the paper 2 questions also. State the conditions necessary for an object to be in equilibrium. So the sum of forces in any direction must be 0. Resultant force equal to 0. And sum of moments, algebraic sum of moments in about any point must be 0. Okay. A wire is used to hold a uniform shelf AB horizontally in equilibrium as shown. The wire is connected to the midpoint of the shelf AB, and this is a uniform shelf AB, so that means this is the point where the weight is at. Sorry, no. And this angled at 50 degrees to the horizontal. The shelf is attached to a wall by a hinge at A. The length of shelf AB is 0.65 meters and its weight is 33 newtons. So this is where the 33 newtons is acting. A cup of weight 1.5 newton rests on the shelf with its center of gravity at a horizontal distance of 0.12 meters from B. By taking moments about A, determine the tension in the wire. Okay, so remember, only this component T sine 50 would be considered because the horizontal one, this one, T cos 50, is the line of action is actually passing through A. So that moment will not be counted. So we have a cup of weight acting at 1.5 Newton also. All right. So moments about A, and this is in resting, so sum of moments anti-clockwise. So sum of anti-clockwise moments is equal to sum of clockwise moments. So you have anti-clockwise only is T sine 50. So T sine 50 times by 0.65 divided by 2 equals to 33 times by 0.65 over 2 plus this one 1.5 times by 0.65 minus 0.12. Anything missing? Okay. So first we calculate this. So 33, oh no. 33 divided by 0.65 divided by 2 plus 1.5 times by 0.65 minus 0.1. So this is 11.52. Then you take sine 50 on the other side. So T would be 11.52 times by 2 divided by 0.65 sine of 50 degrees. So 11.52 times by 2 divided by 0.65 divided by sine of 50. This is coming out to be 46.27, so roughly 46. Take the principle of moments. For an object to be in rotational equilibrium, you have to write the full word over here. The algebraic sum of moments about any point or axis is 0. Okay. A rigid uniform beam rests on a pivot at its center. Uniform beam, that means that this is where the weight was acting. A load of weight 2.6 Newton is suspended from the beam at a distance x from the pivot. A wooden cylinder of weight 4 Newton is suspended from the beam at a distance of 0.4 meters from the pivot on the opposite side of the pivot to the load. Okay, the cylinder rests in a container of the water. The lower part of the cylinder is immersed in water to depth h. Initially, h is equal to 0.10 meters and x is equal to 0.4 meters. The system is in equilibrium. Use the principle of moments to show that the upthrust U exerted by the water on the cylinder is this. Okay. So you have to remember that the tension basically, tension due to this is actually caused by two things: the weight and the upthrust. So the tension over here basically is caused by upthrust and weight. So first off, what we need is the force that is acting over here. And then we can see what is equal to what. Right, okay. So, okay, we have using the principle of moments. So sum of moments is 0. So anti-clockwise moments, that is going to be this one, x times by 2.6 newtons. So 2.6 times by x and minus 0.4 times by t. We'll figure out what U and W are in a second. So tension T is going to be equal to 2.6 divided by 0.4. X is equal to 0.4. X is also equal to 0.4. Okay. So this cancels out. You have 2.6. All right. Now you have tension, sum of force equal to 0. Tension for the this object, tension is also going up, so is upthrust, and the weight is going downwards. So T plus U is equal to weight. So U is W minus T. So that is weight is 4 newtons, and tension we found to be 2.6. So 4 minus 2.6, that is 1 newtons. That's it. Let's make a slightly better diagram for this. Yeah, okay, so that's it. Okay, so state what is meant by center of gravity of an object: a point through which entire weight of an object acts. Two blocks are on a horizontal beam that is pivoted at its center of gravity as shown. At its center of gravity, so that's where the weight was actually going. So the moment of the weight is not considered. A large block of weight, 54 newtons, is a distance of 0.45 meters from the pivot. A small block of weight, 2.4 newtons, is a distance of 0.95 meters from the pivot and a distance of 0.35 meters from the right end of the beam. The right hand end of the beam is connected to the ground by a spring that is an angle of 30 degrees to the horizontal. The beam is in equilibrium. That means sum of forces, sum of moments is 0. By taking the moments about the pivot, calculate the tension T in the string. Okay, so we will need to consider T sine of 30. Basically, sine of 30 is half, so half of T. Right, okay. So anti-clockwise moments is 54 times by 0.45 equals to 2.4 newtons times by 0.95 and plus 95 plus 35, half of T times by 0.95 plus 0.35. You can write T sine 30 also, but sine 30 is half, so I simplify the calculation a little bit. So half of T, so first let's calculate these things one by one. 54 times by 0.45, this is 24.3 2.4 times by 0.95, this is 2.28 plus 0.95 plus 0.35 divided by 2, this is 0.65 t. So t is going to be 24.3 minus 2.28 divided by 0.65. So 24.3 minus 2.28 divided by 0.65. So this is 33.876 Newton, so roughly 34. String is cut so that the beam is no longer in equilibrium. Calculate the magnitude of the resultant moment about the pivot acting on the beam immediately after the string is cut. So remember, if you cancel out this one, if you just forget about this one, so the difference between them is going to be 54 minus times by 0.45 minus 2.4 times by 0.95. This is 24.3 minus 2.28. So that was 22.02, or roughly 22 Newton meter. Okay. A uniform beam AB is attached by a hinge to a wall at end A. The beam has length 0.5 meters and weight W. A block of weight 12 Newton rests on the beam at a distance of 0.15 meters from end B. Beam is held horizontal and in equilibrium. Again, that means sum of forces, sum of moments is 0. String has a tension of 17 newtons and is an angle 50 degrees to the horizontal. State two conditions for an object to be in equilibrium. So resultant force must be 0 and the resultant moment about any point must be 0. You can also write the same thing for resultant force must be 0 in any direction. Okay. Show that the vertical component of the tension in the string is 13 Newton. So we have basically 17 sine of 50. So 17 sine of 50 degrees is 17 sine 50. This is 13.022 Newton, roughly equal to 13 Newton. By taking moments about end A, calculate the weight W of the beam. So end A is this. So the vertical force 13 Newton is acting over here. So, right. And this is a uniform beam and the total length is 0.5. So 0.25 W plus 0.3512 equals to 13 Newton at 0.5. So this is going to be 0.35, oh no, sorry, wait. So 13 times by 0.5 is 6.5. 0.35 times by 12 is 4.2. So this is going to be 6.5 minus 4.2, 2.3. So W would be 2.3 divided by 0.25. So this is 9.2. That's it. All right, so I think we can call it a day over here. Hopefully, the questions were easier to follow, and the working that I did, the explanations I gave were easy to follow. If you have any questions or any uh, points to talk about, definitely hit me up. Reach out in the comments. And yeah, so see you in the next video. Bye bye.